remember I take that V of k equal to that R of k, that is where the k to k plus 1 plus V of k plus 1. V of k plus 1 is k plus 1 to infinity or whatever. Then you move that V of k to the right hand side and you get a 0. And instead of 0, we call that as a Bellman error. And that's same as E of k plus 1. We call that E of k plus 1 as also as temporal difference error in reinforcement learning. The same. Okay, so since it's a finite horizon, you also have to have another error, which is the terminal constraint error. No, this error is 0 if it's infinite horizon. So g hat of k comma n minus gn. So that's this minus that. So we know this, we don't know this, we want to find out. So this theta hat here should also satisfy that when you are trying to find. So you have two errors, you are trying to minimize both the errors at the same time. Okay, so here is the update law. Now there is a little more involved in here, which I think I'm skipping this because you really need to know how you're solving the math and how do you show the proof. Those are in the papers. Yeah, so this is the theta hat. That's the least squares approach, how you get the theta hat. And if you use the theta hat, you can show that the parameters converge. Theta hat converges to theta, the target values. You don't need the target values, but you assume that there exists a target value. That's what in adaptive control we do that. Okay? Any other questions, guys? Any other questions? So you see how I formulated that. So originally we took that matrix. We need to construct the matrix. So that gk xx, gk xu, gk ux, gk uu, and the k, that the Kalman gain kk essentially is gk uu, which is the second row, the last element. That is the inverse of that multiplied by the gk ux, the first element. So at every instant of time, I reconstruct the gk, and then what do? I take that gk uu, inverse that and multiply by the first element. That gives me the gain. So by doing this, I am able to overcome, I am able to avoid the need for A and B. You see? Any other questions? So this is how the dynamic programming, the reinforcement learning, they're all coming together. So because of reinforcement learning, we are able to relax the need for the system dynamics. So my question is, or if you ask me, can it work for any A and B? Yeah. So this type of controllers, we call that as universal controllers. So this is always, we are after that. Yeah. And here the kk is optimal. This is an optimal gain. When you say optimal, that means it minimizes the cost function. So you want to use the cost function as a comparison. If you want to compare two controllers, you define a cost function and you see which controller gives you the minimum cost. Okay? Any other questions? Okay. So here are some mathematical results. You see that theorem 1 shows the bounds on the parameter estimation error. So you see that the initial value is bounded. U0 is an initial admissible control. Remember I said that what is initial admissible control? Policy. And then you see that let update law for tuning theta hat is given by that equation. Then you say that there exists a positive constant learning rate, alpha. That alpha has to be within 0 and square root of half, such that the estimation errors are all uniformly ultimately bounded. And then we show the proof. Theorem 2 shows the boundedness of the closed loop system. So theoretically we show everything is converging, everything is bounded. Now that's the state feedback. Okay, so we can also do the output feedback. Now remember, somebody asked me, I think he just stepped out. So observability. Remember I said controllability is one thing and what is observability. So anybody had looked at what is the Google, I asked you to Google and find out. So the same thing, what is observability? What is meaning of that in a physical term? What is the meaning? That's right, but that's what is observability is. So that means that if I have a black box, remember I keep saying that the black box is my system and my outputs are coming out. So what I'm seeing is I'm seeing that on one end of the output and I'm seeing what is going on inside that black box. Okay? So that's observability. So if you remember, somebody who studied human stomach, I don't know if you realize this is true. One of the physicians, apparently one of the patients had a hole in the stomach. This was, I think, 17th century. So he was able to observe when the food is eaten, he was able to see what's going on inside the stomach. This is what has been done in 17th century. So if you read it, you will know. Okay? So here, basically that black box, the outputs are the things that are coming in. Now, you probably have seen kaleidoscopes. And when you are a child, right, you know what kaleidoscope is, right? There's 3 mirrors and then you put something and you rotate, it forms a lot of patterns, right? So what do? You are watching that through a scope and you are trying to see what is happening inside. You see? So observability actually shows that whether you could see what is cooking inside that black box through the outputs. Now, remember I said that, learning thing. And I'm not going to answer that, you're going to find out, okay, and tell me. So what happens when the process is not observable? So what does it mean? Because you need to know that. Like you said, everybody explains that observability means you have to observe the states of the system through the output. That's no big deal. But suppose a system is not observable. What do you do to make it observable? I think that's important. I'm telling you, a lot of people don't know even that. Faculty. What do you do? So if you ask a person in the industry, he will tell you, not from the academics. So academics usually knows how to test the controllability, observability, that matrix stuff. But essentially, let's say your system has a problem. And you know why? Because what happens is, usually the mechanical guys design something, right? And they just say, okay, electrical guys, the control guys, you're going to do the control. And if you work in an industry, big companies like Boeing or Caterpillar or any of those companies, there'll be a separate group doing the control. There's a separate group that is designing the physical system. Always, okay? So they don't care about controllability and observability. They just design for their own specifications, right? They have certain performance indices. And the controller guys will sit there and have to break their head because sometimes the system may not be controllable. So if the system is not controllable, there's a meaning for it. You can't sit there and do the math and say, well, I can test it. It doesn't work like that. Because they don't care. They'll say this is the best. So a good example is engine. Okay, let's say you have an engine, and the engine, remember that an engine is explained like very simple, okay? Engine is what? Let's say if you are driving an automotive car, you have a 4-cylinder or 6-cylinder engine, for example. Have you heard of that? So you guys take any course, like most of you are AA. Do you take a course on thermodynamics or anything now? No. Right? No. Okay, now, no, nothing. Now they pass them. You don't need to know anything, right? So, no, I'm serious. This is the damaging thing, right? So, very simple layman's language is engine is like a kind of a cylinder with a piston going up and down. Okay, very simple, right? So, what happens is there's a valve which you call inlet valve on one end. There is a valve at the other side of the cylinder called exhaust valve. So, always one of the valves is open. Okay, so what happens is that one end of the piston, there is a piston on, which goes inside. The other end of the piston is connected to what they call crank. It's like it converts the linear motion into a rotary motion. That's basically what that is. Very simple. right? So one of the valves opens, it takes air, you put the fuel. You know, sometimes you have to burn the fuel, there's a spark. In some cases you compress it, and that basically creates a spark. Okay? So what happens is once it creates, it expands, so the piston moves up. And as it moves up and down because of this energy, basically the car rotates, you know, the rotary motion basically becomes the linear motion. Very simple. You see, that has to be that simple, you have to explain. So those days, we have to study. But you remember I told you when I learned all this during my research. Yeah. So if you don't do research, you're no good. So that's a very simple explanation. So you have 4 cylinders. Each cylinder is basically split at about 720 degrees. So one of them will go up and down, then the other one will do, then the third one. So basically what happened, constantly that thing will be rotating, because at least one of the cylinders get fired and it expands. This is how your cars move, okay? Any of those vehicles, most vehicles. So if it's a 6-cylinder, and then you divide the time 720 degrees by 6. Or if it is 4 cylinders, you take 720 divided by 4. So 360 is one rotation, right? I hope you guys are clear about that. So we use 2 rotations, 720 degrees. Yeah. Okay? So remember, you got to have that. So if you don't have interdisciplinary background, so as I said, he is doing control. So control, there will be one group. There will be people who are designing engines and all that. They'll be sitting in a different group. And they never talk to each other. Never talk to each other. So one group does the design, and they do like how to minimize the thermal efficiency, all that, right? You know, waste and all. And then they design something and they'll give it to the control people. Usually the control people are the doubly guys who have no clue. Now I think you probably don't even have a clue. I'm serious. I have done that in Caterpillar when I was doing it. Yeah. So that concerns me. So the controller, so here I asked this question, why? Because then you know what happens, many times the guys in mechanical, they don't understand what is controllability, what is observability. It has to do something with sensors. I'll give you a little hint. When you do the controllability, you do with actuators. So find out what is the physical meaning of controllability and observability. And what happens, suppose the system is not controllable. And you're going to find that. You see? So you can't go and say that my matrix is not working or something. In most cases in engines and all, there's no mathematical models for the dynamics. Okay, so here is the observability. So observer, you know, you have an observer, you're assuming it's observable. Observability, controllability is, how do you test the controllability for a linear system? What is the equation? So controllability is always with A and B matrix. So AB, AB, A square B up to A into the n minus 1B, right? So what is the observability? C, CA, or C, CA, whatever, in the, yeah. But that we know, but we don't know what it means. So that's a danger, serious, yeah. So you have to produce engineers, but not mathematicians, remember that. You need to know the mathematics, but as an instructor, you got to produce, you got to teach engineering, not the mathematics. So they know what happens. Yeah. So that's why we import, right? In India, pretty much everything gets imported. I don't know, I think I shouldn't say this, but one of the attendees, he was saying they build all these things. But you know what? I've seen most places I visited, they just import everything. You know, missiles, everything from outside. Yeah. This is very unfortunate. That's very unfortunate. We have very brilliant minds. All of them are in the US. Yeah. So, but I'm just saying that disconnect, that mathematics to the physical thing is what I'm asking you. What is the meaning of observability in a real situation? What is the meaning of controllability in the real situation? So what happens when you don't have that? Let's say you test it and it doesn't work. What do you do? See, that's very important. And if you're working in industry, it's your headache. Yeah. They'll tell you it's your headache. So mechanical guys, they do their design, like an engine, for example. They do that based on their own specs, and their goal was to minimize the losses, like heat losses and stuff. But it's your headache to design a controller for that engine so that you put in the fuel and it minimizes the fuel and it generates the amount of heat energy which is converted to the mechanical energy. That's your headache. But so the first thing you do is, how do I design a controller? So then you need to know what is controllability, what is observability. But what happens when that system is not observable? What do you do? Yeah. So I'm also a faculty. Remember that. So you guys teach controls? Yeah, I think you should be careful. So if you want to really make a student, remember that. You really need to know that connection between the math and the physics. This applies to everybody. Okay, so I won't tell you that, and I want you guys to find out. And then there are a lot of brilliant minds here, faculty, so I thought I would let them go. So here is the output feedback. So we are using an observer. So that means that you only have the outputs measured, you don't have the states. Okay, so I still want to use the Q-learning. I still don't know A and B. Remember that. I still don't know A and B. So in this case, it's not network control system, just the, first let's understand this without network control. So I'm using an observer. Remember that A and B are assumed to be unknown. C is known. So here you can see, here is my observer. I'm estimating A. I'm also estimating B. So this also is unknown. So I'm adding yk minus c times, this is basically like a Leuenberger observer. Okay, standard Leuenberger observer. All right, so this L hat, you have to make sure that A hat minus L hat times C or whatever has to be observable. Okay, then you can actually find a L. So basically you convert this into error. This is the error equation, x of k plus 1 minus this, you get A minus LC times x tilde plus this. Now this term is basically A hat, B hat multiplied by x hat and UK. This is the basis, these two terms are unknown. So now you see that how I converted this into an adaptive control problem. So this is the unknown parameters, which basically has A hat and B hat. This basis functions is x hat and U, which you know. Okay, x is you don't know, but x hat you know. All right, so now what you do, you see that this term is A tilde, B tilde and L tilde. These are unknown, and this psi is got x hat, U and y tilde. We know y tilde, we know U, we also know x hat because that's a mathematical equation. Okay, so this is how you formulate the problem. All right, then you basically come up with an auxiliary error with some data. So you take the data from k minus 1 previous history, and the same thing you do that, you can write it like this, and here is the update law for the observer. If you update it like this using this data, then actually you can show that everything converges, and the parameter estimation error, that is the target values which you don't have to, and the actual values, you are showing that they eventually become smaller and smaller and converges using Lyapunov. Okay, so you can see, then you can use the Q estimator on the top of it. This is the theta hat I showed you. This is the total error. Total error means the terminal constraint error plus the Bellman error. Remember, we had two. One is the Bellman error. You also have the terminal constraint error. So E total is basically the total of those two, sum of those two. So you use the same Q-learning using the output feedback. Okay. So you can see that here is the state feedback flow chart. This is the output feedback flowchart. So in the state feedback, you initialize the value function, you compute the Bellman equation, Bellman error, terminal constraint error, then you use the update law to update the parameter weights, then you basically unpack it so you get the G hat, then from the G hat you compute the optimal policy UK hat, and from UK hat you find whether you have reached the final time. If it's not, K equal to K plus 1 and you go back. K is the sampling instant. Okay? If it's an output feedback, you still initialize the cost function, U equal to initial admissible control, V naught equal to 0. You first update the observer, X hat, then you update the estimator, then you use the G hat, Q learning, and then once you get the Q learning, you check whether K equal to N, you reach the final time. If not, you go back. Okay? So that's the flow chart of state feedback versus the output feedback. So let's take an example, F16. So how many of you heard of F16s? So what is F16? I know he knows. So we also import, right? Pretty much everything. Mirage, everything we import. So what is F16? Huh? Fighter jet. So I know Trump was trying to offer F-35s, right? Yeah, that's more recent ones. So F-16. So this is the linear dynamics of an F-16 aircraft. Okay? So you can see that this is the A matrix, X, B matrix, U. So here is my cost function. So now my sampling interval is 0.1 seconds. Weighting matrix Q, R, and SN, they're all identity. Then we use the polynomial of time to go with saturation. The saturation is mainly not to let the basis functions to blow up, okay? So now you can see, I'm plotting here the system response, the states. The states converge. You see that goes to 0 for regulation. This is the control inputs. It goes to 0. And you see the cost function error. It goes to 0. And look at that. I have two errors. One is the Bellman error. Other one is the terminal constraint error. So what I want to show you is I show this. They all goes to 0. So when they go to 0, you know that's basically means that it is optimality. Yeah. Okay. So therefore we basically show that it's converging. It works. Okay. So that's the conclusion. Okay. So now we apply the same thing for the network control system. The only difference is in this example, the loop, you guys have seen it, it becomes a AZK, which is ADK in this case, and then you have a BDK. These are stochastic and time varying. You see? But the process is identical, what you did. The Q learning, we use the same Q learning, except that it is basically that AZK, BZK has the random variables inside that, but it works. Okay? So, you know, these math equations are very scary, but it's not. Basically, this is a standard bunch of equations, like you're trying to minimize it. You have the E there, which is the expected value, because that is the stochastic. And you want to make sure that the average value reaches and is bounded. Okay? So that's it. That's it. So you see the R has got the xt, q, xt plus. So all this is very sim. So here is the one of the constraints. This is the temporal difference. Okay, so the notations are different, so people scare you and write more papers, but it's the same thing. So here, this is the terminal constraint error, the second one, because this is a finite horizon, is equal to 0. And from there you get the optimal control, which is E R inverse B times partial V star, where V star is the solution to the Bellman equation. If it's nonlinear, it becomes a JB equation. Okay, so all that derivation is there. Eventually, okay, so stochastic solution to the certainty equivalent SRE, stochastic Riccati equation. The reason is certainty equivalence is you're assuming that there is a process noise, and we're assuming those terms you don't care, and so it's a certainty equivalent of stochastic Riccati equation, and the control input evolves backwards because I'm not using Q-learning on this, right? And for finite horizon, the control gain becomes time varying. We already saw that, even in the standard case. So we really need forward in time solution, okay? So if it's a linear network control system, the system matrices are stochastic, time varying, and unknown. We already saw that, all right? And the disturbances and the process and measurement noise are considered absent, just to make sure it's simplified. Otherwise, it becomes more laborious. That's all it is. So here is now let's go to the network control systems. So there are two types of delays. One is the delay between the sensor and the controller. And there is other delay from the controller to the actuator. There are two sets of delays. Okay, so the sensor to control delay is kept less than one sampling interval. The sum of two delays is bounded while the initial state of the system is deterministic. This is a very standard assumption. Now, remember, if the delay is more than a sampling interval, what does it mean? So what does that mean? It becomes open loop. So that means that for two sampling instance, you don't have any feedback. And it becomes open loop, sometimes the system can become unstable. Yeah. So you have to make some assumptions. So you can see that for a wide area network, two types of delays are considered independent, ergodic, and unknown, whereas their probability distribution functions are. So this is what I was saying. You don't know exactly the delays and packet losses, whereas you say that they belong to a distribution. Okay? So then you derive the dynamics. We have seen this. Okay, and then you get that AZK and BZK, and you can see that AZK has got that packet loss and then the delay. So we have seen this equation. Okay, and we also, I told you, if the original system is observable and controllable, then the network control system is also observable and controllable. Okay. Then we use the Q-learning. Because this is a linear system and we're going to use the Q-learning, the process is very same as what we did. So linear network is time varying and higher dimension because you are using an augmented system. So because of the augmented system, the AZK, this dimension of this matrix is different from the original system. Because you see that there is this vector, the ZK, essentially has XK previous values of the input all the way to D bar. So depending on how many values, delayed values of the input you take, that dimension of that vector changes. Because that changes, AZK has to be accommodating. So therefore, the dimension of that matrix AZK will be different. You see? Okay? So don't forget that. If the original linear time invariant system is controllable, then NCS is also controllable. We have proven that. That's in the first chapter. I skipped it, but you know. So you do this process is identical explained to you. Okay, so this is a finite horizon. We got to do a little more math. I'll show you. So if there exists a positive definite function L of the linear with strengthened condition that if this L of x of k plus 1 minus L of x of k, if it's less than or equal to minus of alpha times L. Now why is that minus is important? What does it mean by minus there? What does it mean? Yeah, it's the same as a differentiator. So L of x of k plus 1 minus L of x of k, if you divide it by the time interval t, that's your derivative. So what does it mean by L dot less than or equal to minus alpha times L? So the system energy is decreasing. The Lyapunov function is nothing but your energy. So how many of you guys read about Lyapunov stability? Huh? I see many of you nodding. So do you know much about Lyapunov, the guy who developed this method? Huh? Yeah, and you know, this guy is a very brilliant guy. I'll tell you something. This is a very good lesson. So you get excited. Look, this guy is so brilliant, okay? Everything is energy. Nothing, you know, the Lyapunov stability is nothing but energy. Okay, and remember we did that in high school. You know, energy can be neither be created nor destroyed. So it transforms from one energy to the other. So the Lyapunov stability basically takes some kinetic energy and potential energy bundled together. That's your total energy. And you're looking at how the energy is being dissipated, right? And you know that when the energy becomes zero, just like a human, you basically become immobile, right? You just stop, right? You don't mobile. So that's your equilibrium point, right? So that's what that is. So the minus sign basically shows it's decreasing, and ultimately it just stops at some place where the energy becomes zero. Okay? So in terms of Lyapunov, this guy is so powerful. So the difficulty with any of the proofs is finding that Lyapunov function. So we spend a lot of time trying to find the Lyapunov function to show that the first difference becomes negative because that is decreasing. And you know what happened? He died before he told how to find that Lyapunov function. There are some things that people use, but those are basic, like quadratic functions, and you try to do that. But in a general system, it's basically, so it's a sufficient condition. That means that if you use a Lyapunov function, you prove it, it works. But if you cannot prove it, doesn't mean that the system is not unstable. That's the problem. And he passed away before he was able to tell the world how to do it. And it's been more than 100 years. Nobody is able to come up with a way to find it. So if somebody finds it for a given system, he will be a big deal. 100 years, nobody is able to do it. So always we use some sort of a ad hoc way or a heuristic way to find the Lyapunov function. Yeah. So that's a very powerful, and I think, I don't know whether you know, this guy is a Russian mathematician. So 1955, Russia was ahead of space, you know that. Sputnik and all. US was behind. So it's basically Kennedy who did that. And you know what people didn't know was the state space. So there is a guy by name Parkes, 1955. He wrote a paper. He translated the Russian into English. That's a very classical paper. And Russians were far ahead. And he did that. That paper is classic. So my advisor had on his board. Everybody, control guys, have that. That's a very classic paper. So that paper was published in 1955. Then people realized what the heck is going on. How do you do that for multi-dimensional systems? Because in order to send a satellite, it's a multi-input, multi-output systems. So you need the state space representation, and Russians were far ahead. So this Park, that paper was a classic paper. He understood that a little bit on the Russian side, and then he converted that to English. And then all these people started working on it. Ackerman, all this came after that. Yeah. So then US guys were sent the thing, you know. Yeah. So they were far ahead at that time in terms of all this. So Lyapunov is a big guy, honestly. Unfortunately, he passed away. So we still struggle to come up with a Lyapunov function. If you know the Lyapunov function, then you probably have a solution. The challenge is coming up with a Lyapunov function that is positive definite, and the first derivative or the difference being negative definite. Okay. So in any case, in this example, so you see that L of x of k 0 and 1, then is negative definite. Then for any time instant, that L of x of k can be expressed in terms of bounded initial Lyapunov function L of x of 0 and a constant alpha. So this is basically bound. But if k goes to infinity, if I stretch it, then you see that that L becomes 0. That means the bound will become 0. Then it becomes asymptotically stable. Okay? So we were deriving all this with my students. So here is a Q function. All this is pretty same, except that you have a E. See, otherwise this whole derivation is same as what I showed you before. You see that the bottom, you see there is that ZK and UK, that H matrix that we talked about. Now we call that as expected value of psi k, because this is a random, with random variables. And use the same Q learning, and you show some properties, it converges, and all this stuff I can skip, because now here is AZK and BZ. Okay? What is going on? Okay, so here is the model free tuning. So you see that model free tuning is there's no targets. So this is the value function. You write it using Kronecker product, but except that you have the expected value. That expected value over the delays and packet losses. Okay, this is the notation we use. This is the terminal constraint. So here is the unknown parameters. Here is the basis function using Kronecker. And basically you do that adaptive control. You convert this into an adaptive control problem, and then you come up with the update law. So there are two terms. You see, this is the Bellman error, and there's also final constraint error. So this mathematics sometimes will confuse you, but it's the same steps that I did, except these are stochastic. Bellman and terminal constraint error. Now why do we need a terminal constraint error here? Why do we need it? So why do we need the terminal constraint error? I already explained it. That's why I asked you this question. I see everybody kind of staring. Now why do we need two errors? Remember, there are two errors. One is the Bellman error, other is the terminal constraint error. Now why do we need the terminal constraint error? It is a finite horizon. Finite horizon, you have a terminal constraint. If it becomes infinite horizon, that terminal constraint error will become 0. Don't forget that. So that's why it has both Bellman and terminal constraint error. The only thing is the formulation is in terms of E, which is the expected value. Otherwise it's the same. And then you construct the historical Bellman residual, and you come up with the same update law that I gave you. So everything now is mean, AE error, boundedness, and so forth. Because remember, we studied in the morning, asymptotically stable becomes asymptotically stable in the mean. And that's what we are doing. Okay. And then you show the optimal control input, the same equation. You see that the inverse of that multiplied by the other term times the ZK. That becomes the UK hat. Here is the flow chart. The flow chart is same as the deterministic case, except that you have the E. Okay. So you have the terminal constraint error, you have the Bellman error, and then you come up with the update laws. You update it, you construct the U hat, and then you basically change the time. So the code is there. I gave you the code. You guys can play with it. Okay, these are all theoretical results. Here is a table that basically gives you the stochastic optimal regulator. Here is the controller. So you can see in there, this is the Q function estimator. It has two errors, Bellman as well as the terminal constraint error. So you see the Bellman equation error, the terminal constraint error, that's going in. You're constructing the matrix H, and from there you're unpacking it, and then you take the bottom row, the diagonal element inverse of that multiplied by the first element, and that gives you the KK, the Kalman gain, which is L hat K. That's your optimal policy. You apply that to the system. So here you don't need A and B. So the same idea that you did with a deterministic system, you are extending that to the network control system, stochastic. And that's the only difference. Otherwise, it's just identical. The notations are different, but otherwise the same. Okay? So let's take a different example. So in this case, it's a batch reactor. It's a linearized version. Batch reactor is a nonlinear system. but this is a linearized version, just like F16. Okay? So you have the A matrix, you have a B matrix. This is a matrix, not a vector. So you assume this is unknown. So I used the initial, so here is the augmented state, x of k, u of k minus 1, u of k minus 2. So this is a 3 by 1 augmented system. Okay? So here is the initial admissible control, u naught. So remember that I said what is admissible control? Admissible control is to make sure that it makes the cost function what? Huh? Finite. The cost function finite, less than infinity. And so you need to start that. That's the right, we call that as a right initial step. So sometimes it's very difficult to find this. Okay, there are ways to do it, but it's very difficult. That's one of the problems with it. You can relax it. The former student Travis, he did that to relax it, but the Lyapunov proof becomes really cumbersome. You can relax it. But the problem is, if the system is unknown, always people ask this question, how do you determine the initial admissible control? Yeah. If I don't know AZK, BZK, how can I come up with the initial admissible control? Homework. So check that out. So how to define the initial admissible control when AZK and BZK, when the system dynamics are unknown? Okay? So I'm going to ask you tomorrow, like, one at a time, and I'm going to call your name. So better you spend some time. So I'm going to call your name and say, hey, tell me what you found out. So make sure you spend some time after the class. We're going to end at 4 o'clock. And you spend some time trying to read the material. I think he's going to send you the slides. Read the material. Search the Google. Got it? Okay. So the question is, if I don't know the system dynamics, how do I determine initial admissible control? You understand that? Yeah. Okay. So here you see that the regulation errors converge, the control inputs go to 0, and look at that how quickly they converge. So basically it learns pretty quickly, very fast. Okay. And you see that there are two errors. One is the Bellman error. The other one is the terminal constraint error. It also goes to 0. So the total estimation error is basically the Bellman error as well as the terminal constraint error. And when n goes to infinity, that means that the final time is stretched to infinity. That means it becomes finite horizon. Is it finite? Infinite horizon. Right? That's what that is. Okay, the errors always go to 0. So this is the total error goes to 0. Now look at that. I compared the cost. There are two plots here. One is proposed ADP, Adaptive Dynamic Programming Based Optimal Design for unknown NCS. The second was traditional optimal design with known NCS dynamics. So I want to compare the traditional method. So that means that I assumed that I know all the delays and packet losses. I want to see whether my approach, which is unknown, works close enough. So you can see that. So this is the red is basically everything is known. And my blue is basically AZK and BZK is unknown. So there is an error, right? There is some error. That's why you see that error. But what happens as the time progresses, within about 1.5 seconds, you see how both of them converge and they become 0. It's very fast. Okay. So now you can actually look at the effect of Q matrix, Q and R. Q is basically used to weigh the X transpose QX, the state. R is basically used to weigh the control input. Remember I told you in the morning, if you crank up Q, that means you really want the X to converge very fast. In a tracking problem, it's like E minus X desired. When you crank up Q, that means you want that X minus Xt quickly to go to 0. If you crank up R, basically you want the U to be small as possible. Okay? So you can see here, So I hope we have plotted different values of q, 0.1, 1 and 5. So as you crank up q from 0.1 to y, see the 0.1 is green, red is 1, and look at the blue, it's 5. So what happens? The norm of the states will become quicker, go to 0, much faster. As the same way, if you crank up, so those are weighting matrices. So as you crank up, you drive the system faster. Now tell me guys, what happens when you crank up? What is the drawback? What is the drawback? Everything has a, there is a saying, no free lunch. Have you heard that before? No free lunch. That's what we call. So, like, when you see sales, here also in the malls they put sales, right? Really is the sale that guy is putting as a sale? No. Basically, sale means he's not going to go bankrupt, right? He basically still makes money, but it's not as much money as when he basically no sale. But remember, a lot of people try to go and buy it when they think, oh, it's 20% off. Is that what you guys do here also? Because in US, people are mad about it. But what they don't realize is that guy is smarter than them. He's not going bankrupt, right? He puts on sale, so people come and buy it. But actually that means that, look at this cost, is much higher. He's basically jacking up the price. Yeah. That's what he's doing. Okay? So what is the drawback? What I'm saying is, oh yeah, you can raise those Q's and R's as much you want, but where do we pay the price? Remember, engineering is a bunch of, you have to satisfy so many things. You can't just increase. That's why I said no free lunch. When somebody is taking you for lunch free, there is a reason why. Okay? So that's what it means. Nobody is going to give you free lunch. So the same thing with any of the design, there is always trade-offs. You cannot arbitrarily raise some of the values without paying something penalty. So this is your homework now. So what is the trade-off? Why can't we change the value, So that's important because there are reasons, and you guys can play it with in your code. Yeah, try it out. Okay? And this is important because you will do this. If you're in industry working, we have to do it. And now remember, these students, deliberately they're adjusting those values so you get a very nice result. Right? That's always happens, right? Because they never will go to a professor and show them a bad result. I never saw a student coming to me and say, it didn't work. So I think it's always important to, to vary those values and try it out. Okay? So this is important. There's a lot of trade-offs. Okay, so extend into infinite horizon. I think this is tomorrow's lecture. We may take a break? Yeah, that's fine. Excellent. So we'll take a 5-minute break because I think we'll try to cover this also. Huh? Oh, that's nice of you. the procedure is identical, like you do in the finite horizon. Okay, so here is the Bellman equation. You remember that E stands for the expected value, and then you use the least squares. You first construct the history, because that's the data from the reinforcement learning, and then basically once you get it, you are trying to minimize the error square, E square, Bellman error, and you take the gradient and you want to drive it to 0, and that's what the update law is. Okay, so you get the update law, and see, you end up in getting like this. So this is basically exponentially stable. The error goes to 0 by using that this update law. That's what it's basically showing you. Okay, so then Bellman equation in terms of the estimation errors. So you do that in terms of the theta tilde. Theta is basically the G matrix. You're converting into a vector by using the Kronecker product, right? And then you basically write in terms of the Bellman error, and then you pose it as an adaptive control problem. You come up with that update law, and the goal of the update law is to drive that G tilde to 0. Remember that. That's what we are doing here. And so what you can say is convergence of the stochastic cost function with adaptive estimation error is demonstrated given an initial admissible control policy. So you still need the control policy initial value to be admissible. Remember that. If you have only stabilizing, it's not enough, because the cost function has to be finite. The linear NCS time varying dynamics are shown to be asymptotically stable in the mean. So basically the errors go to 0, and it's asymptotically stable in the mean because the mean error goes to 0, not the instantaneous error. That's the difference between stochastic and a deterministic. Okay? Overall stability needs to be proven. You have to show that and use the Lyapunov. So here we show that, and we show the convergence of that, and you can see as k tends to infinity, the E of z of k goes to 0, E of theta tilde of k also goes to 0, V hat converges to V, and E of U hat, expected value of U hat, the optimal estimated optimal control policy converges to the true optimal control policy. So that's what the theorem basically saying. The proofs are in the book or in the papers. Take a look at it. Here it says refer to appendix 3D. Probably there's an appendix in the book that should have the proofs. Those are Lyapunov proofs. Okay, so here is the update law, or the table, which essentially shows here is the optimal control policy in terms of H. Then you compute the Bellman error, and you compute the parameter estimate, and then you go back as k becomes k plus 1 and so forth. So asymptotically stable in the mean. I just give you revisiting the definition. An equilibrium point is said to be asymptotically stable in the mean if there exists a positive constant r for every initial condition. You pick x of t naught less than r such that E of x of t minus x of e goes to 0 as t tends to infinity, where the norm denotes the Frobenius norm, and this expectation is a mathematical expectation. So that's how you define asymptotically stable in the mean or asymptotically stable in the mean square. People use either the mean or mean square in the stochastic domain. Okay, and then you can also do ultimately bounded, uniformly bounded in the mean or in the mean square. You can do both. Mean square means that norm, the expected value of x of t minus xe, you have a square there. Then you show that that term basically is asymptotically stable in the mean square. Okay, and it comes out like that when you do the Lyapunov proof. So check the proof. Okay, so I think let's see here, what is this? So this is the same thing that for infinite horizon you build the H matrix. Okay, you don't have terminal constraint error. Then you have the update law. You see that temporal difference error, j hat minus j hat of k minus 1 plus r, that's the temporal difference error. So these slides I added so that you don't have to flip your notes. You can actually use the same thing, you know. And this is a deterministic case, and here is the way you relate this to the actual optimal control input, and then overall stability for infinite horizon. You take the batch reactor example 3.2, you should have a code 3_2 in that MATLAB code. So it's a batch reactor. You can see in the batch reactor I have the A matrix. Here is the B matrix. This is continuous time. Now we have incorporated the network effects. You see the delays? This is the random delay. You see that this is for the other one. So we assume the sampling interval is 0.1 second. The bound on the delay is 2, d bar equal to 2. The random delay's expected value of sensor to controller is 0.08 seconds. Expected value of the controller to the actuator is 0.15 seconds. The packet losses follow Bernoulli distribution. These are all coming from stochastic control theory, you know. So you see that that's the packet loss. When it goes down to 0, that means packet is lost. So this is a Bernoulli distribution. Okay, so packet is not lost and lost. Lost means it goes to 0. So basically you create in the simulation, and you guys could check it. So we create that, and here is the initial admissible control. Okay, and this is this is somebody else's work. So this was one of the works of my advisor. This is my work. I'm kind of comparing it. Regression function and parameters. Remember, this is the Kronecker function as part of that H matrix. Okay. So now look at that. If I don't consider the network imperfections, the optimal control blows up. And why does it blow up? Because the traditional optimal controller cannot handle when you have delays and packet losses. You understand that? So that blows up, right? So since the network imperfections are considered, let's say if I consider them, assuming that everything is fine, nicely, you see that how nicely it converges. Okay? And here is the value function. So you will see when you plot it, you start anywhere here, you're trying to minimize it, and ultimately you reach the bottom of the valley. So I don't think you have these plots in the code, but you can write by yourself some MATLAB, and then you basically show that you know where it starts, and you see the trajectory going all the way down, and it reaches the bottom of the valley. You see that? It's like it either sides, and then it comes, and then that's where the bottom is. That's the minimum value. Now remember, I don't know, have you told about the assessment at the end? Okay, so the understanding between him and I is, it's going to be very tough, and most of you, majority, has to really work hard to get the assessment. So make sure that that's how we discussed. So you may want to spend good amount of time going through the slides, running the MATLAB code, play with the code. Remember that. That's why we spend a lot of time, essentially making sure that you play with it so you understand it. Got it? So there is an assessment. This is last. So like an exam. How many of you know there's an exam? So this is the estimated Q function. So basically you want to see, you can actually plot that Z1, Z2 and start the initial value, and you can plot the trajectory. And as the controller is working, you will see that it tries to minimize that and show that it reaches the bottom of the valley. It's showing that the minimum value, okay? And here is the regulation error, and you can see that there are two plots. One is the adaptive estimator error based optimal control, and the other one is AE based suboptimal control. Now what is the difference? Optimal control is basically the finite horizon. The suboptimal is the steady state solution. You take the steady state gain after it converged, and you use that as part of the control input. So because of the steady state, you're using the steady state gain, the cost is higher than the time varying gain that you are using. So the time varying gain basically gives you the lowest cost. But why do you use the suboptimal? Because suppose you cannot compute it in real time. Let's say you are unable to compute because the gains are changing with respect to time. Then what you can do is, a lot of industries this do. They run this code offline, and they find out the steady state value of the gains after they converge. They use those steady state value in the control input. So what happens is, it's a little bit higher than the optimal cost, but it's better than if you are not using the optimal controller design. So let's say you're using pole placement. You understand what pole placement controller, right? So if you do a pole placement controller, like on that day we were talking about desired poles, and then you place that, you are not optimizing it. Always the suboptimal is better than the pole placement controller. And the benefit of a suboptimal is the controller gains doesn't have to vary with respect to time. That's the benefit. Always the optimal controller gains vary with respect to time. Remember that. So if the gains are a matrix, that's the problem, because you need computing power. And when you are doing it in real time, that the matrix has to be updated, because the gains have to be updated every sampling instant. But let me say this to you. We implemented many, I used to think that you need a powerful computers, okay? Always I go back to my childhood, right? When I was an undergraduate student. Now I think people hardly knows this. So you know 8086 processors? Do you use 8086 now? No. So we have implemented observer, neural network, actor and critique. If you have time, I'll show you some demos, okay? On an 8086 processor, it works. This is a formation control of mobile robots. So 8086, the only difficulty we had, my students were implementing, is the memory requirements. Because the neural networks have matrices, right? Remember that. We were using single neural networks. So those matrices, basically we are swapping it, because we don't want to save all those matrix values, you know? So we have to swap, and when we were swapping it, we had trouble saving those matrix values, because we had an observer, we had an actor, we had a critique. So we were able to implement in 8086, I think it's a 8-bit or 16-bit processor. 16-bit? Yeah, 16-bit processor. So some of this, what I'm teaching you, you can do that. I have many implementations hardware. And I do for Boeing, quite a bit of Boeing implementations, aerospace systems. So, yeah. So we have time, like he said, extra time, you know, but not today. We have the cricket match, but if we have extra time, I can show you some videos where these were hardware implementations and stuff. So that time we may have to turn off the video recording, you know. So I can show you some hardware, hopefully, okay? So you see the difference between the two plots. One is suboptimal, other is optimal. Suboptimal means you take the optimal controller, you run it for a long time, and once it converges, the gains converge. You can plot the gains, it converges. Once it converges, you take the steady state optimal gains and you use them instead of the time varying gains. That's what we call suboptimal. Okay? All right? Okay. So here is the difference, you know, AE based optimal and suboptimal. Control inputs, difference between the control inputs. There are a lot of plots here. Okay, so I will leave skip that part, and I think that's all we did. So we kind of went fast. We were 10 minutes ahead of time. Thank God to India versus Australia match. So any questions, guys? We have 10 minutes. Any questions? Some issues, because when you do that, there are some approximations and all that. This basically gives you to bring in the protocol effect. So you are bringing in that network as part of it, and you can study attacks, security problems. And the computer science people are not knowledgeable, right? Because we know about the system behavior, overshoot, undershoot. So when you attack one of those things, it really causes problems, right? But the CS people don't understand that. So there are a lot of things this type of modeling opens up. The security is a big deal. And you know probably how Americans got access to Iranian centrifuges. Do you know that story? Oh, you don't know that? Oh, you're missing something. Okay, so you know that they want to know how Iran was developing the nuclear thing. So what they did was they had the PLCs. So PLCs are not as good as other embedded processors. So they bought PLCs from Allen Bradley or one of those companies, the American companies. So they nicely wrote a software program that goes around and accesses all those things. So they were monitoring in secret the nuclear things, what they were doing, and they were slowing it down without Iranians knowing it. It's a big deal. It's published. Yeah. So they were creating some attacks to slow down the centrifuges from the nuclear, so that it doesn't become a kind of a grade, plutonium or whatever they were using. That you can build a nuclear, whatever. Yeah. So the PLCs are much more problematic because it doesn't have a lot of security. That's why. So when you deal with all these systems, network control and all, on one side is good, on the other side, I had some slides in the intro, I skipped them. Maybe we'll cover them in the part of the future. You can actually create some signals and you can attack a sensor or actuator. So I don't know whether you know, probably it might be of use to you. So there is a guy who is very smart, and there were real things here. So one of the guys were like, a lady was driving, he's shown on the real TV. He said, I'm going to control that car that lady is driving. It's an American car, and he had it with his laptop, and he controlled it. That lady who was driving on the highway, she lost control. She doesn't know. She was trying to turn the wheels, but the car is not doing, so I have a video. So people can actually control the vehicles if that particular, how he got involved? Through the canvas. So there are some danger things when you have a network inside the feedback loop, and if that network is a wireless network, it's even more dangerous. Somebody can eavesdrop and they can vary those parameters. That's what is happening. In that case, the lady lost means basically she didn't crash or anything, but she couldn't control the vehicle, and it's already being controlled by the guy remotely. She was trying to brake it and it's not braking. Yeah. So a lot of things. There was a Boeing aircraft. He was using that monitor. Remember, on a plane, if you travel long distance, you have a little thing on the screen, and somebody went through the screen and controlled the plane's speed and other things. They arrested him. Oh yeah, very smart people, but in a bad way. So there is a danger when you have a network inside that loop. The danger is basically there's a security threat, and that's a problem. So you got to be careful, because let's assume that you have to drive a process control. You are using a network-based process control. Imagine if somebody really want to cause a damage, they can really change some things, right? And so let's say if Tide or some other soap are being made, you can change some parameters, and that basically comes out garbage. Yeah. So there is that, it's good in one way, network control systems, but there are also some bad stuff can happen. So I skipped that few slides. Maybe when we have a closing session, I will go back. Okay? When we have time, I can play some videos. So we also did some attacks. We call that as resilient control. So when there are attacks, how do you basically, so somebody can vary the sensor values on the fly, or somebody can change the control values. Yeah. Think about it.
So another one is you are giving initial admissible.
Right.
Admissible control is one thing.
Right.
What is initial admissible?
So initial admissible means the initial value is to be in the right selection. It has to be admissible for that system. And if you don't start with that value, the subsequent values that the network or the controller is going to generate will not be admissible. Okay, so
in case I have seen that X0 with initial condition X0, and you should have a U0, so initial some equation has to be satisfied.
right. No, it's not the equation. It's basically the admissible. That just has to be admissible. There's no equation there.
Over that was required, but depending on the initial condition, a particular U is required.
That is correct. Okay. And the reason you need that is because as you are computing the further future control values, it has to make sure that the future values are also admissible.
Yeah, because all the time once the equation is satisfied.
Right. But if you don't choose the initial value, there is no guarantee that the future values will be admissible. So that these controller designs assume that the U naught, which is the initial value, is deterministic but admissible. So mathematically, then only you can prove that the further values you are computing U1, U2, they will be continue to remain as admissible.
So initial, if it is admissible, rest of the other
That is
will be
correct.
admissible.
Okay, any other questions? It's 4 o'clock, yeah.
So there were two metrics given on. So
Right.
if we are increasing the value of 2, then it will go to system deviations.
It will go to what?
System deviations.
Right, x. So it actually forces the x to converge to 0.
And if you are increasing the R matrix, then it is going to give a power effect on control power.
That is correct.
Then if suppose I have to deal with real-time systems, like some gust is coming from inside, so then at that time we can't decrease the matrix because I need the
Right.
optimum performance.
Right.
At that time, how can I use neural control?
Yeah, you can adjust that in real time, but typically we don't want to do that. So what you do is typically, in most cases, you play with those before you deploy them. And you want to look at it, what are the trade-offs? So what will happen when you really try to increase the Q value or increase the R value? So what I mean is, you really want to find out what is your limits. But I don't think you want to vary it in the kind of a missile scenario. You don't want to do that. Because in order to do that, you have to have a wireless or some sort of a communication, right? And imagine if you can do it, somebody else can also do it.
But in aircraft case, it must be. Because you have to deal with the dynamics and distance.
Right. No, but what I mean is, I don't know whether you want to vary them because you want to fix them. But you want to first see in the simulation how those values affect. I think it's this noise.
I think interfacing. You come closer to the speaker.
Oh, speakers, it's a basic interference. Alright, any other final questions, guys? Alright, so I think I'm going to stop here.
Yeah, we can close.
We'll close it. Tomorrow we have a lecture in the morning, 10 to 12. In the afternoon, there's a tutorial, right? So the tutorial will have the background on Lyapunov stability and also running the MATLAB code. So we just be around and you guys run it, play with it. It does work, we have proven that. So you run it and see what are the extremes. But what I suggest is before you run the MATLAB code, go through the slides. Dr. Dera is going to provide you. I would encourage you to just spend a little time. I try to, don't worry about the detailed math because I think we didn't go through those details, right? But I suggest you to see how the Q learning is done and how we basically were trying to overcome the A and B. Remember that? And how the optimal stuff is, we are claiming is optimal. Those kind of things you want to try to understand that. And what are the variables that you can adjust so that when you run the code, you can try to vary multiple times, make sure that you don't keep overwriting it, then it's very difficult. But what I do is you comment out and vary some values and see what happens. Now remember, I told you before, you won't get exactly what I showed you on the slides. Why? Because there's randomness, remember that? So there is a thing what they do with the stochastic variables they call Monte Carlo simulations. Have you heard of Monte Carlo? What does it mean? What do you do in Monte Carlo? We repeat the experiment with different initial conditions. And then we do what?
Then we see within the region what are the results.
Right. You basically average them. So that's what you do. So some of those results have been ran 10,000 times because that's how we present them. So that's why I said when you're running them, You may not get exactly the same plots, but it will be very generic because you're also initializing the initial value sometimes. That also has some randomness. So this is basically how it's different from a deterministic system. In a deterministic system, you run it always, you get the same result. Okay? Alright guys, I'll see you tomorrow at 10 o'clock.